¿Cómo? No, sí, me encanta, me encanta. Son bacanes. Me gustó mucho el curso de Villana, pero...
Yeah, sure.
Welcome everyone to the afternoon session. The organizers wanted me to remind you that if you'd like to join the dinner on Friday, please write your name on the list up front. They need to make reservations. Our first speaker is Leonard Gehrman from the University of Bielefeld. He'll talk about towards Großkolomm-Zagier theorem for practic points.
Yeah. Thank you very much for the introduction, and thank you for inviting me here. I mean, to this great place and also to this wonderful conference. And you will notice that the theorem I'm going to talk about is inspired by the mathematics of a lot of people here in the audience, as you will see later. So everything I'm going to say will be either joint work with Michele Fournier or joint work with Michele Fournier and Marty Rosette. And let me start a little bit with motivation, so what I'm going to do. So I start with A, an elliptic curve, over some number field f. And so you all know by the model-Weyl theorem, that the f-valued points of A is, of course, an abelian group, but model-Weyl tells us it's a finitely generated abelian group. And yes, I'm calling the elliptic curve A and not E. I'm sorry for that. It's a finally generated group, so it's isomorphic as a group to a bunch of copies of Z to some rank, which I call Ra of f times something finite. And then, I guess I should switch here. Natural question you can ask is, what is this rank? So given an elliptic curve, what is this rank? This is already maybe hard. But even harder is there a systematic construction of Ra of f many linearly independent points on A, or in A of f. So by systematic, I don't mean, of course, you can start with an elliptic curve and try to get all the solutions, but by systematic, I mean something like you start with an that works somehow for all elliptic curves or a huge class of elliptic curves at once without knowing anything about the equations you have or so. And of course, this is hard and maybe possible. So an easier question you might ask is, can you at least systematically construct a non-torsion element in the top exterior power? So the exterior power over f of A of f. So this module has rank 1. And so it may be easier to construct canonically elements in there because you just have a one-dimensional space. And the question is, can one construct non-torsion elements in there in some systematic way without knowing equations of A, or so on and so on? OK, so that's still very hard, maybe impossible, I don't know. So, but let's switch to the case where we know stuff when the rank is equal to 1. So we have the rank 1 case. And it's the theory of Higner points. Okay, so what you're going to do is probably you want to say that f is totally real. You have a nice theory of Shimura curves over f, and you want to say that A is modular. So of course over the rationals we know every elliptic curve is modular, but in general maybe we only know it's potentially modular, but whatever. So what this gives us is some modular parametrization where this x is a Shimura curve over f. So this is associated. So I'm only considering quaternionic Shimura curves. So this is somehow associated to a quaternion algebra. Better. B over f split at only one place at infinity. Okay, so modularity tells you that, I mean, you can't take, like, this already appeared in Gonzalo's talk, you can't take, like, any quaternion algebra. There are some restrictions. I mean, you can always take the split one. Oh, there is no split one in the setup, maybe, over f. But, I mean, let's assume you can find a nice quaternion algebra. Then another thing you can do. Now you want to construct algebraic or f-rational points in A, and the mantra is it's easier to construct something on f-rational points on Shimura curve, which is not quite right. It's easy to construct algebraic points over some quadratic extension of f. So if you have E over f, an imaginary or totally imaginary quadratic extension, plus some Higner condition with respect to this quaternion algebra I've chosen here. So it's something to do with the set of primes ramified in B and the set of primes ramified in E and, well, the ramification of A. So there's some kind of conditions that I'm going to ignore during the talk completely. You get a bunch of points, maybe indexed by some elements in the class group of E. And they live in X, HE, when now this is the Hilbert class field of E. So these are CM points. I mean, if you're working over the rational numbers, then here we would have something like the modular curve. So it's the moduli for elliptic curves, and you could just think about elliptic curves that have Cm by this thing E here. I mean, for general Shimura curves, it's maybe not, you don't have a nice moduli problem for that. You may want to embed it into some kind of, or connect this with some kind of unitarian PL Shimura variety where you have a moduli problem, and then consider those, or just believe in the mantra of Cm points. Okay, but you get points like that. And what you can do is now push all these points forward into your elliptic curve, take a sum over all of these, and then, in fact, it will be an element in A of E. And maybe this is what I call P of E, this Higner point. Okay. Somehow we can always at least, or under some conditions, always construct one point in there. And it really governs the rank 1 situation almost completely. So what's known is known. So if this point PE is non-torsion, then the rank of A over E is equal to 1. So especially this point is a generator of the model value group. So, I mean, I should put here a lot of names. So maybe that's, but let me first say Kolyvagin and Nekova. So Kolyvagin did this over the rationals, and I think the most general form is due to Nekova over the totally reals. Correct me if I'm wrong in the history. And so in fact, this relies on an earlier result. Somehow this point PE, or it's the height of that point, is related to the first derivative of the L function of A over E at 1, and this is due to Gauss and Zagier and Zhang, and maybe Zhang and collaborators in the most general form. Okay, so actually you first prove a statement like that, and I mean, okay, that tells you, well, and I mean, it's, you don't only have like this one point, but you have like a whole tower of points, so kind of an Euler system, and that you use to prove the second thing. In any case, so, okay, so, and if you believe in the Birch-Swinnerton entire conjecture, the order of vanishing of the L function should be the rank, so everything somehow fits together nicely. And so if, in addition, so if the rank of A over F, if you already know that this is equal to 1, right, then you know that basically this PE is an A of F, maybe up to torsion. Yeah? It's in here for all E. I mean, either they are 0, by 0 and non-torsion, I mean the same. I mean, I maybe tensor with Q all of the time in the end. So all this PE are generators of the same one-dimensional vector space. And so there are, you get Q linear relations between all this, between the PEs. But in fact, this thing was known before the work of Kolyvagin and Nekova. And so in fact, what do I want to say? In fact, we have this theorem that maybe so depending on the case considered, either theorem of Gauss-Zagier, Borchardt, well, one Zhang tells us we look at the certain generating series, PD to the Q to the D, where PD is like the Hegner point of discriminant minus D. So if minus D is fundamental discriminant, it's just the Hegner point I just introduced associated to this quadratic extension. So this is a Hilbert modular form of parallel weight 3/2, and it's in Shimura correspondence to the Hilbert modular form corresponding to A. And actually, I may put a plus here, so this PD plus just means I take PD plus the complex conjugation. But so this will really be something that lives in A of F. But as we have seen, I mean, either these are all 0 or they all live in the same space, or it doesn't really make a difference somehow to put this plus here. Okay, and so because you know maybe that there's I mean, the famous one about, where he introduced Borchardt products.
How does it? Okay.
I mean, so maybe about the history here. No, I mean, so let me first say a couple of words in here. So the strategy here is, and so Gauss-Consorguet did this for the modular curve. And what they did is they computed somehow the height pairing between different Higner points. So what Borchardt did was he showed modularity of certain special cycles for orthogonal Shimura varieties over Q, well, special devices, I should say, like modularity in the Picard group. And these are exactly the special devices. They come out.
So those are the devices of Borchardt's product.
Yeah.
Borchardt's product. So there
Yeah.
exists a weakly holomorphic form for which,
Okay. But you can't apply Borchardt to the totally real setting, so there is no Borchardt lift there. But what Wang Zhang are doing is actually, they also prove a statement for more general class of orthogonal Shimura varieties over the totally reals. And in fact, for higher dimension, it's kind of easy, but because a certain Chern map is injective, and you only have to prove some modularity in homology, and then you do intersection to get it back to the one-dimensional case. No, that's it appeared in Compositio. It's like on Gauss-Consorguet's theorem over totally real fields, I think it's the name. Yeah, so maybe a little bit of history, but somehow all these proofs are rather different.
Now your Q points are taken to be on the curves or on the other.
Which one?
The Higner points.
I mean, these are on. I fixed the Shimura curve, and these. Yeah, they all live on the Shimura curve. Yeah, I fixed the Shimura curve somehow once and for all. Okay. Okay, maybe that's the story in the rank 1 case. All right. So what happens in higher rank? No, okay, it's a Hilbert modular form on, I mean, these points live in a finitely generated abelian group, right? And you could, I mean, say it's like a Hilbert modular form with values in that finitely generated group, or you could say like for every homomorphism to C, the now like generating series with coefficients in C is actually a Hilbert modular form for X3 half. Right. Okay, so we had Shimura curves and somehow these CM points, and I call them CM zero cycles here, and we got elements in A of E, these Higner points out of them, and they are somehow related to a first derivative of the L function attached to A over E. And I asked like the question to what happens in higher rank, but you could also first ask the question what happens in lower rank. So what's happening in the rank 0 situation. So maybe you want the actual value of the L function. And then, so this, here we looked at Shimura curves corresponding to quaternion algebras which are split at exactly one place at infinity. You could look at, and this is wrong terminology, I know. I call it a Shimura set, but this corresponds somehow to a quaternion, totally definite quaternion algebra. And you can look at somehow special points here. So this is just a finite set, and there's somehow special CM points on here as well. And, well, this gives you just elements in Z somehow, in a way, which is the batch 0 of A of E. And they are related to the by Waltz-Furget's formula, or by formulas by Waltz-Furget and other people, to this L value of A over E. Okay. okay, so here you start with this totally definite quaternion algebra. Here you have a quaternion algebra split at exactly 1 prime at infinity. So, I mean, the natural guess is you take here quaternionic Shimura curve, Shimura variety, sorry, of some dimension r. And here, I mean, this corresponds to the situation that you have exactly r places at infinity where this quaternion algebra is split. And there is still a nice theory of 0 cycles, or CM 0 cycles on here, corresponding to, again, quadratic extensions. And so we would like maybe that you can produce out of this data something in R's exterior power of A of E. And maybe this is already too much to ask. And maybe you want to replace this by some global cohomology group, Galois cohomology group. And you have a Kummer map from A of E. Sorry, this is too low. So maybe you want to do something like that. And this is possible if you believe the conjectures of Nekova and Scholl. So Nekova and Scholl have these conjectures that there is somehow, for these quaternionic Shimura varieties or more general Shimura varieties, that there should be more symmetry than directly visible, meaning that, for example, you look at your étale cohomology. This is computed by some kind of complex where your Galois group acts, and they actually conjecture that there is an extension of this action to a larger group. If you believe their conjectures, you can actually produce classes in here, but I think nobody knows how to tackle these conjectures. So, I mean, so there's a big question mark here, how to do that. And so what Michiel and I did, maybe like 3 to 4 years ago, is to somehow look at a p-adic shadow of the situation. And I should have said that the conjectures of Nekova and Scholl are called the plectic conjectures, and these things should be the plectic points, the images of this map, whatever that is. So, and we try to cook up some local avatar of these points. And so the idea is, so you want some extra data. So you want somehow, well, let's say, given set f s of primes p1 to pr over some chosen rational prime p, and such that you want your A to have multiplicative reduction at all P in S. So that's one condition. And the second one is that this E over F is inert at all P in S. So that's the kind of assumption. And then under this assumption, we produce a point, let's call it PES. And unfortunately, it's not living in some kind of exterior power, but it's living in the following beast. So you take, for every prime in your set S, you look at the EP valued points of A. So this is a topological group with a p-adic analytic topology. And actually, it's more or less a finitely generated ZP module times something finite. So what we do now is take the completed tensor product over these things. Or you could just if you throw away the finite part, we don't care about torsion. These are just ZP modules, and you take the tensor product over ZP. That's what I mean by this completed tensor product here. So we produce a point in there. Yeah. Well, okay, sorry, I didn't say, but of course the R's derivative should show up somehow here. But I mean, that doesn't follow from the plectic conjectures at all. I mean, that the things you construct here has anything to do with L values. Okay. And actually, I mean, the way I phrased it, I deleted it. That was a mistake. But for example, you could think you're over some totally real number field, and you know the rank is 1. So you already know everything is controlled by Higner points. But for example, you could still look at a Shimura surface and do this construction and get this strange element, but like the second exterior power is 0. So whatever you construct there via this Nakovaschol mechanism won't have nothing to do with the model Weil group at first. I mean, we don't know how to construct this thing, so maybe all these things would be 0, but I mean, it's hard to conjecture something about an object you can't construct. So. Without testing anything. But in any case, all I wanted to say is maybe that you construct some garbage also that's not related to the arithmetic of the elliptic curve. In any case, so we have this point, and I should first say some remarks. No, you start with, well, and then plus some Higner hypothesis. So, I mean, maybe not every set is allowed, but I mean, these are the minimum requirements plus some technical conditions that I dropped. Yeah. Okay, so in the case S is equal to 1, we actually just construct a point in A of EP1. So in this case, so this PEP is just your usual Higner point. So, I mean, A of E sits just inside A of EP. And this is, I mean, Bertolini, Damont, and Mock. So actually, somehow this is now in reverse order in a way. So, in fact, how this project kind of started is that, so this whole construction here is somehow p-adic analytic, and Bertolini, Damont over the rationals, and then Mock later in the totally real situation, gave a p-adic analytic formula for these Higner points as seen in the local points. And somehow we stared at this formula, or rather Michele stared at this formula for quite some time, and then at some point he thought, well, I think I can generalize this, assuming that a couple of things hold, and I could just say, well, but all of these things hold, so we can construct it. But the way this is done for S, I mean, greater or equal to 1, so what are the steps to construct this point? I don't want to go through the whole construction is. So first, use p-adic uniformization of the quaternionic Shimura variety. So maybe this is due to Warszawski or Brutu-Think in this case. So, I mean, you want this multiplicative reduction assumption here so that you can find your elliptic curve or you want to find a Jackie-Langlands lift of the automorphic representation associated to a quaternion algebra where all these p's are ramified. And this is possible under this assumption. because for and somehow you want it one of dimension r somehow, or where the associated Shimura variety is dimension r, and then you can use the p-adic uniformization to write this. Well, maybe at first you have something like your Shimura variety is of a form some well, r copies of the usual upper half plane modulo gamma, and you somehow want to see, so these are the c-valued points. You want similar story for the cp-valued points, and you want to write it as r copies of the p-adic upper half plane modulo some gamma prime. But this gamma prime now will be a subgroup of a quaternion algebra where you switch somehow what happens at infinity and this set S. So this gamma prime will live in a totally definite quaternion algebra that is split at all these primes here. So there's, well, something going on here, but I don't want to go too much into detail. So you first use this p-adic uniformization result to then purely work on this local side. Purely, you forget that there is like a global Shimura variety. You just work with this kind of object. And then, well, your Jacobi-Langlands lift gives you a modular form on this space. And here, modular forms are the same thing as so-called boundary measures. I mean, this, I guess in the case r is equal to 1, you can read this in like the books on Van der Put from the early 80s. But the same strategy works here as well. And then you do some p-adic integration on functions whose divisors somehow correspond to these CM points on HP. So that's like a very rough way how to do it, which won't matter the rest of the talk. OK. Good now, but now we've constructed this element in here. So the next question is, what does this have to do with global points, right? So what you also can look at, following determinant map from the wedge R of A E to exactly this thing, tensor product A PR. And so what you do, you send a wedge of R points, should be 1, to just the determinant of, well, you take the embedding associated to P1, so the first prime of, well, let's call this X. Otherwise, there are too many P's on the board. So you take your first point, embed it in the first coordinate here, and do this up until the rth point. And here you take all the different embeddings. So just to make it clear what's happening, in the case that size of S is equal to 2, you send x1 wedge x2 to take the first embedding, x1 tensor with the second embedding of x2 minus, well, the other way around, the first embedding of x2 tensor the first embedding of x1. Then what we conjecture is that, and conjecture is somehow if you have enough points, so if the number of points actually bigger or equal to r, such that this space is not just 0 anyway, then this point PE S is in the image of the determinant map. And maybe you have to tensor with Q. So maybe there are some denominators because we weren't careful in constructing these points. Okay. And this is again related to this thing that happens in the conjectures of Nekova and Scholl. Maybe that you can construct these Plaktic Hegner points via the machinery of Nekova and Scholl if their conjectures hold, but maybe they have nothing to do with the model Weyl group directly because the model Weyl group is too small. Same thing happens here as well. And if this point, if moreover, so we want this assumption, and if moreover the point is non-zero, or non-torsion, I should say, then the rank is actually equal to R. So this is the top exterior power that we consider. Okay, you can always conjecture stuff. So what do we know? So evidence. Okay, if S is equal to, consists only of one element, then we are in the realm of Hegner points and everything is known. So we are in an algebraic situation. So then I claim that there is a numerical evidence. This is a lie. Yeah. So as I formulated everything now, this is just a blatant lie. So what's going on is, all this construction somehow can be made purely in terms of group cohomology, and then you can do that Damon has done like 25 years ago. You can replace a totally imaginary quadratic extension E over F by an arbitrary quadratic extension, and still run all of this process. There's no nice theory like p-adic uniformization anymore in the background, but somehow all the formulas you write down make sense for an arbitrary quadratic extension. And then this numerical evidence is in the case where the base field F is real quadratic, and the quadratic extension over that is ATR. So it's not exactly in the CM situation. So anybody who knows how to compute stuff, please also compute the situation that should be easier at first, the one of CM points, but nobody has done this so far, and I can't work with computers, so I don't know how to do it. But luckily, we have theoretical evidence. Namely, in fact, we can relate this point to some R's derivative of an anticyclotomic p-adic L function. So we have a Gauss-Sargé style theorem, but now you have to replace the usual L function by a p-adic L function, or rather an anticyclotomic one. And of course, here you have to look at a certain logarithm of this point to really get it as a derivative. And also the statement like this is again a lie. It's not written up in full generality. So what you have to do is maybe, on each of these factors, you have a Frobenius operating, right? That's the Frobenius of E of P1 over F of P1. All of these primes very nerd. And what you can do to your point is somehow you have, for each collection of signs, you have a projection now of these points to certain eigenparts of the Frobenius. And if you take the complete plus projection to all plus eigenparts, or to the complete minus projection, you get a formula like this. And for the complete minus part, these R's derivative is really in the anticyclotomic direction, and for the complete plus part, for those who know, is in the weight direction. So you expect that the complete point is somehow the derivative. You sometimes have to take derivatives in partial weight direction and partial anticyclotomic direction to get the full point. But it's not written up yet, so I shouldn't claim this. But the minus part, so this is due to Michele and myself, and the plus part is due to Hernandez Molina. What? NER, yes. Okay. And you can actually use this to prove the conjectures in very degenerate situations. So you get a somehow proof of conjectures in base change situations. And what do I mean by that? Well, I mean, this algebraicity conjecture is very hard because, I mean, to test it, you somehow have to produce points on A of E, and as I said, this may be hard. But there are certain higher ranked situations where it's very easy to write down points because, for example, you can consider an elliptic curve over Q, take the base change to some real quadratic number field where the prime P is split, and then take as E F to times E naught, where E naught is an imaginary quadratic field over P, where P is inert. Then you're exactly in a situation like that. But what you realize is that in that situation, well, you have the Higner point corresponding to E. Well, let's assume we have this F over Q. So yeah, P is P1 times P2, sorry. P splits. And we have an E naught over Q imaginary quadratic. Then you can just look at E naught times F over F. And in that situation, you can prove that this PE, P1, P2 is really just, well, and I never wrote the subscript A anywhere here because A was fixed, but here now I introduce it. Sorry for that. You take the Higner point of A over E naught, and you wedge it with you twist A by this quadratic character corresponding to F, and look at a Higner point at E naught. So these will both define points on E-valued points of A somehow. And this will, so the determinant of this wedge will be the point PE in good situations. Yeah. So in good situations. So in good situations here, I mean, what we're using is the first result. So on the minus part, so we want that these Higner points are really, we're in a situation where A and AF have no rational points, or the groups are torsion to get this machinery running. I mean, basically, one uses, well, you uses a formula like that, and then a p-adic Artin formalism for these p-adic L functions to get rid of. So that's not that hard as soon as you know these Grossagé type formulas. Okay. I spoke too long about all of this because this is all old news. I mean, so so now suppose we are in the situation that this R that's floating around is already the rank over F. Right? So we already know that. Let's assume that. And we assume we are in the situation. So we always fix somehow this Shimura variety. And once we fix this and all this data, then all the points with the Higner hypothesis will have the same sign of the functional equation. So, and we assume that we're in a situation, assume that there is no sign change by going to E. Right? So what you expect generically is that the rank doesn't change. Of course, it can change, but generically, it really shouldn't. There's no good reason for doing that. So in this case, and by the conjectures, you expect that somehow there is like Q-linear relations between all this PES. Right? They all should come from the same global algebraic element, more or less. Okay, so, and the theorem, and I should say very much in progress. I mean, not a single word has been written up yet, but yeah, we discussed about this for quite a while now, together with with Michele and Marty, is that you can again look at such a generating series, and this is again is a Hilbert modular form of parallel weight 3/2, and it's in Shimura correspondence. There's a with a modular form attached to A. So we assume that A is modular, so there's a Hilbert modular form of parallel weight 2, and there's a correspondence between parallel weight 3/2 and parallel weight 2 forms. And here, again, somehow P of D should be sort of PDS, and here's a plus missing, sorry, there should be a plus here everywhere, is like P of EF dash minus D. If D is like a fundamental discriminant. Okay, this is a very rough statement. I mean, and if you put enough assumptions, maybe square free level and so on, the space that you get is essentially one-dimensional and defined over Q, so you get Q linear relations for all of these points. So you actually show that yet all these elements defined by p-adic analytic means corresponding to all kinds of quadratic extensions in this huge p-adic module, you show that the thing generated by these is at most one-dimensional over Q. So that's like a corollary of that. Okay, so yeah.
No, you are not in the best situation, it's in general.
In general.
So when you assume this much sign change,
Yeah.
why do you expect correlations between?
No, I mean, I just expect that somehow A of E is essentially A of F for almost all E. I mean, and so, I mean, the exterior powers are the same. So, I mean, if the algebraicity conjecture holds, they should all come from this one element that exists here. So they are all just multiple of a given thing. So really, the algebraicity conjectures would imply that these generate a one-dimensional space. And we can actually prove this. So if you know algebraicity for one quadratic extension and where it's non-zero, you know it for all somehow. Again, this is for any R. No, this, I mean, yeah, this could be. I mean, it seems like the strategy doesn't really notice the R in a way, but it could be that you just construct a zero series. Yeah. I mean, in Shimura correspondence, I should say, like, it's a this could be just zero. And then saying it's in Shimura correspondence is a bit like.
Yeah, what do you mean by this? How is it related to the Shimura lift?
I mean, this is just a multiple of the Shimura lift.
Ah, it's simply a multiple.
Yeah. But the multiple could be zero. Yeah. And I should say, well, there, as stated like here, this is, I mean, again, a lie. So probably we have to make some simplifying assumptions. But one assumption that's not simplifying is that, every P in S. So A has split multiplicative reduction for all P in S. And again, this is an assumption. If you want this no sign change assumption, this is also good, because if you have P that is non-split multiplicative reduction, and then over all these E's, you would suddenly get split multiplicative reduction. So locally, at least, you have a sign change. So in any case, so that's really an important assumption. And maybe in the last, let me check, 10 minutes, I try to sketch a proof. Yeah, I still have 10 minutes. Great. So now you can, yeah. I mean, D, it's any admissible fundamental discriminant. I mean, just any positive. I mean, you could first say like just any positive, totally positive element in a totally real number field, like just the pure series. And then for the fundamental discriminants, you exactly get these Higner points I talked about. But actually, you could introduce these plectic points with some additional level and so on, and you would get all of these. So I put that under the rug. So what's the sketch of the proof? For most part, or you don't have to know what plectic points are. So, so what you're going to do is, so I already told you that somewhere in the construction, there's a quaternion algebra split at all P in S and totally definite. So this is lurking somehow in the background. And so you can look at V, which is just the elements of V of trace 0, together with the norm. And this is a nice three-dimensional, totally definite quadratic space that already showed up in Gonzalo's talk. So he already told us that somehow, okay. You have automorphic representations of B star, maybe modulo center, so F star, of some weight. Here, maybe drop the F modulo F star because we have even weight and it's true. So you have automorphic representations of some weight 2k here. Then call it theta k. While you're looking at theta series, you have a map here to Hilbert modular forms of weight 3/2 plus k. So that's one part of the theta correspondence. But actually, again, this B star or B star modular center is the isomorphic to the special orthogonal group of this quadratic space, and you're really using the theta correspondence here. But thankfully, in this setup, everything is made very explicit by work of Gonzalo and co-author Ziroli. So this is like yeah, this made explicit. I need more space here. Sorry that I can't write down your name. So this is one thing, and then there is a fact. Because we have the split multiplicative reduction assumption, and the algebra split at all this P and S, what you get is, if you look at the theta k, or it's really theta 0 of GA. So again, this GA is an automorphic representation on here of weight 0, that is the Jackie-Langlands lift, Jackie-Langlands of this FA. This is just equal to 0. It's a general phenomenon here, and you can't do anything about that. So usually what people do is you look at this theta lift and put all these primes where you have split multiplicative reduction into the ramification set of B and then work with that. But we are really using that this thing is 0. Because what's happening next is I should really say, I mean, made explicit by Tonaria. Theoretically. Okay, and Schiroli, right? Well, shouldn't get my names wrong. No, Schiroli, okay. And somehow the next fact is, and basically you can use old work of Stevens for that, is you can put, first you can put this GA into a p-adic family. So instead of over-convergent cohomology, so for example, you can use work of Urban. I don't know if in this specific example it was worked out before. You can put it into a p-adic family, and you can also put some of the theta lift into a p-adic family. So let's call this maybe GK. And then you can look at this GK, which is just theta K GK. So this is a p-adic family of half-integral weight forms. And it's another fact. So, and we know if we specialize to k equal to 0, this vanishes. But even more is true. Another fact is and this may be sorry. Daniel goes first. So at least I learned this from a paper of Mladen, Daniel, and Andre. That in fact this thing is 0 as long as Kp is equal to 0 for one P and S. So what I haven't said is that for every somehow, let's assume for the moment that your prime is like completely split in F, and also that the set S consists of all primes, just for simplification. Then there's a one-to-one correspondence between embeddings, so this thing that parameterizes weights, and the primes P and S. So somehow you can pick one direction, and this really corresponds to 1 prime P. And as long as Kp is 0 for 1 prime, then this thing also vanishes. So this family vanishes on a lot of hyperplanes somehow in weight space. And so what I learned from the paper of the 3 people is that if you have your p-adic family and you vary at some primes, but stay fixed at a given prime, and the given prime is, you have a Steinberg representation there, and you vary, then it stays Steinberg at this prime. That's what I'm using here. And so this fact I said before, that some theta lift vanishes, this is just true anytime you have like the split Steinberg representation locally. And so we just assured that this just happens all the time. So you have big space, and what you get from here is if you take somehow the derivative in every weight direction of this thing, and then evaluate at k equal to 0, this is somehow the leading term of your p-adic family at k equal to 0. This is a classical Hilbert modular form of weight, parallel weight 3/2. It's a p-adic modular form just because it vanishes there somehow. And it's more, I mean, you can check that it's ordinary and then, it's classical somehow. And let me tell you, I mean, this is somehow the unique leading term. You have to take a partial derivative in every direction, otherwise the thing just vanishes. This is a canonical object to study. And so now maybe, so let's just call this G prime. So what's these Fourier coefficient of G prime? Well, you just take these derivatives of the Fourier coefficients of these theta k of some gk. So this is part of the family.